More recently, the Sudbury Observatory, located in a mine underground, has made a breakthrough by measuring neutrinos, known as antineutrinos, the fundamental particles emanating from the nearest nuclear reactor. Previous experiments have used a scintillator, an oil-like substance that makes a jump of light whenever electrons and protons pass through it. Neutrinos and antineutrinos are tiny particles, like the building blocks of our universe. They play an important role in monitoring nuclear reactors and detecting nuclear activity. Scientists hope that this will lead to the possibility of a large and inexpensive array of reactors to ensure that countries comply with nuclear weapons treaties. The proliferation of neutrinos and antineutrinos indicates that they are a fundamental element in the entire structure of the universe. Their detection has been a problem for a long time, due to their rare interactions with other material particles and the impossibility of just taking a picture. Nevertheless, they can be used to study a variety of physical phenomena and to analyze distant astronomical objects, as well as to monitor nuclear reactors and detect violations of nuclear agreements. Every second, around 100 trillion neutrinos pass through our bodies unnoticed, and although they pose no threat to humans, their properties could be useful in many fields of science. Neutrinos are most often produced as a byproduct of high-energy nuclear reactions, collisions of protons and other particles. Antineutrinos, according to Joshua Klein, one of the leading experts, are usually created artificially, such as in nuclear reactors, as a result of radioactive interactions aimed at splitting atomic nuclei. For this reason, nuclear reactors can generate large amounts of antineutrinos, making them an ideal target for research. As Klein says, measuring the antineutrinos of reactors can determine whether or not they are on, and possibly what nuclear fuel is being used in the process. Scientists believe this could be useful for monitoring energy production and weapons-grade material. The method could also be used to monitor whether production is being switched from a power reactor to a reactor that produces nuclear weapons. The assessment can be done with just one reactor, allowing many large but relatively cheap dedicated facilities to be built to ensure that countries are meeting their obligations under, for example, the Nuclear Weapons Treaty. Reactor antineutrinos have very low energy, so the detector must be very clean, even with traces of radioactivity. In addition, the detector must be triggered at a low enough threshold for the particles to be detected. The scientists also specify that for a facility located 240 kilometers away from a nuclear reactor, it is especially important to have at least 1,000 tons of water in it. Although neutrinos and antineutrinos are difficult to detect, these elementary particles are essential to our universe. Thanks to them, scientists can better understand what happens in stars and other objects in space, as well as learn the basics of physics, including the weak force of gravitational interaction. In addition, neutrino research can help unravel the mysteries of the origin and evolution of the universe. Finally, these elementary particles can be used in medicine to detect cancer.